Hello everyone, my name is Dr. KCH Apparao, working as an associate professor in mechanical engineering department. Okay, in previous classes, we discussed the questions and some numericals which are given in the question bank, mainly on heat exchangers. Now we'll see question bank questions or question bank discussions on radiation. So mainly we'll see black body laws. What are the different bodies? What are the different laws of the radiations? We'll see. So this is very important question. First of all, we'll see what is the impact of radiation. You know that radiation for conduction and convection we require the medium. So conduction occurs due to the vibration or lattice movement of the electrons. Convection occurs bulk movement of the particles from one place to another place, either by naturally or by some external agents. So in both cases, so medium is required. But in case of radiation, without medium, heat transfer takes place. For example, heat transfer from sun to moon or sun to earth. So, because it occurs due to the phenomena of electromagnetic wave phenomena. Okay, so we'll see electromagnetic radiation. So there are many types of electromagnetic radiations in which thermal radiation is only one. Okay, regardless of this type of radiation, we say that is propagated at the speed of the light, that is 3 into 10 to the power of 8 meter per second. It means so the speed is equal to the product of wavelength and frequency of radiation. So C is equal to nu lambda, you know this one. So C is nothing but speed of the light. Okay, so wavelength lambda and nu is the frequency. The units of lambda may be centimeter or angstroms. 1 angstrom is equal to 10 to the power minus 8 centimeter. Okay, 1 micrometer is equal to the 10 to the power minus 6 meters. So a portion of the electromagnetic spectrum is shown in this figure. You can see in which the range of thermal radiation it is 0.1 to 100. You can observe here. Okay. Well, the visible light portion of the spectrum is very narrow. Visible light spectrum. So this is visible light spectrum is very narrow. Okay. So extending from about 0.35 to 0.275 micrometers. You know this one. So the propagation of thermal radiation takes place in the form of discrete quantum. So energy transfer in the form of quantums. Okay. Each quantum having energy of E is equal to h nu according to Planck's theorem, where h is the Planck's constant and the value of this one is equal to 6.625 into 10 to the power minus 34 joule second. Okay. So by using this one, you can find out the electromagnetic emitting energy h nu. Okay. So this is the mainly radiation is the phenomena of electromagnetic wave phenomena. We'll see what is radiation. Energy transfer across a system boundary due to a temperature difference. You know this one. No, it doesn't depend upon the molecular movement or molecular vibration. Only temperature difference. Okay. So by the effect of electromagnetic wave phenomena or electromagnetic wave emission, all bodies radiate energy in the form of photons. So energy transfer takes place in the form of the photons moving in random direction with random phase and frequency. So when radiated photons reach another surface, they they may be either be absorbed or reflected or transmitted. So the emitting energy on any surface, so that portion of emitting energy or incident energy. So it may be either absorbed by surface or some portion will be reflected or some portion will be transmitted. Okay. So the behavior of the surface with radiation incident is upon the, it can be described as follows. So absorbivity, that is represented by alpha. It means the fraction of incident radiation absorbed. Rho shows the reflectivity. Tau shows the transmissivity. We already discussed in previous classes also. Radiation heat transfer is the distinct separate mechanism from the conduction and convection. We know that one. It refers to heat energy emitted by bodies because of the temperature difference. Okay. All bodies at a temperature above absolute zero temperature, so emit energy by process of electromagnetic radiation. Okay. The intensity of such radiation is depend upon the temperature difference and the nature of such body. So properties of the body and the temperature difference, both are very important. The energy transfer by radiation doesn't require any medium in radiation process. Okay. The energy transfer by radiation is the fastest at the speed of light, and it doesn't suffer any attenuation even in vacuum. Okay. So these are the few points regarding the radiation. We know that there are two theorems of radiation. One is the Maxwell theorem and Max Planck's theorem also. According to the Maxwell theorem, okay, the energy is transferred from hot body to cold body in the form of electromagnetic waves. Okay, so you know this one. The electromagnetic waves passes energy emitted by body as a result of changing electronic configuration. Okay, electronic configuration of atoms or molecules. The electromagnetic waves are characterized by either frequency and wavelength. You know that. So C is equal to H or lambda is equal to wavelength C by nu. C is equal to, you know that, 3 into 10 to the power of 8 light velocity. Okay. So according to Max Planck's theorem, the propagation of thermal radiation that takes place in the form of discrete quantum energy, heat energy transferred in the form of the quantums. Emitting energy is equal to H nu. So H into C by lambda. You know that H value. Okay, these are the formulas. First law we'll see. The first law is equal to so that is the Max Planck's law. We'll see this law. According to this one, you can find out the emissive power, black body spectral emissive power. So what is, we'll see what is black body spectral emissive power. The spectral or monochromatic emissive power for a black surface is it is highest at every wavelength at any given temperature. So it is given by Max Planck's distribution law. Okay. So based upon this law, we can find out the emitting energy at particular wavelength. So maximum emitting energy at particular wavelength. So this is the formula. The final formula. So C1 and C2 is the constants. So you see. Then so this is the formula. Next to spectral emissive power, it is represented by V lambda. So it is the amount of radiation energy emitted by black body at an absolute temperature T per unit time per unit to surface area per at a particular wavelength. Okay. you can observe this one. So wavelengths, then emitting energies at particular wavelengths. So next one is the Wien's displacement law. This one also very important. Okay, for radiation, measuring the radiations. So according to Wien's displacement displacement law, it provides the wavelength where the spectral radiance has maximum value. The spectral radiance has maximum value. So by using this law, you can find out the wavelength. So lambda max. Okay. So where spectral radiance has maximum value. So this law states the black body radiation curve for a different temperature peaks at wavelengths inversely proportional to the temperatures. So these are the different wavelengths. So that is inversely proportional to temperature. This is the formula is equal to maximum wavelength is equal to Wien's displacement constant by temperature. So this Wien's displacement constant is equal to 2897 and lambda. So you can, by using this formula, lambda max is equal to 2897 by T. So then you can find out the temperature. Then temperature is equal to T is equal to 2897 by lambda. If you know that lambda max, then you can find out the temperature at particular wavelength. If you know that temperature, then you can find out the lambda max also. Okay, so these are the formulas. Maximum spectral emissive power. So emissive power at particular maximum wavelength. Okay, so that is the lambda max temperature T is equal to 289. You know this one. This is the formula finally. So EB, maximum spectral emissive power at maximum wavelength, at particular wavelength where emissive power is very maximum, that is the value is equal to 12.87 into 10 to the power minus 10 T to the power 5. So you have to remember this one. Okay. So C1 and C2 constant, we know this one. You can refer this one. Next law for radiation is the Stephen-Boltzmann law. It is very important law. We know this one about. So you know the Stephen-Boltzmann law. So rate of heat transfer is proportional to 4th power of the absolute temperature. You know this formula. It is the total emissive power of a black body. So it is used to find the total emissive power of a black body. It is represented by EB, total emissive power, not at a particular wavelength. So it gives the total emissive power of a black body. It may be obtained by integrating equations, Planck's distribution equation over the entire wavelength. Okay, so not particular wavelengths, entire wavelengths. It means EB is equal to integral of 0 to infinity EB lambda, monochromatic wavelength, spectral into with respect to lambda. Then we will get this formula. So this is the EB lambda, you know the formula, this is the formula EB lambda. So C1 and C2 constant. If you simplify this one, we will get that value, that is nothing but EB is equal to total emissive power of a black body is equal to sigma into T to the power 4. So the Stephen-Boltzmann is nothing but total emissive power of a black body is directly proportional to the 4th power of the absolute temperature of the body. Okay. According to this law, the radiation energy emitted by black body is proportional to the 4th power of its absolute temperature. If you know that absolute temperature, we can find out the rate of heat transfer through that black body. Okay, so Q is directly proportional to T to the power 4. So then EB, emissive power of the black body, sigma into T to the power 4. You know that sigma is a Stephen-Boltzmann constant, 5.67 into 10 to the power minus 8 watt per meter square Kelvin to the power of 4. So this is the value. Okay. So you know that this one already discussed in first chapter. If the radiation takes place between any two plates, the temperatures of first one is T1 and T2, and heat transfer rate Q, then that is equal to the view factor, safe factor is equal to F. Then and the area, if you consider the both of area of both plates A, then W is equal to sigma A into T1 to the power of 4 minus T2 to the power of 4. So emissive power, rate of heat transfer in the black body between the two plates, two black bodies. Okay. So this is the formula. We can use this formula to find out the rate of heat transfer between the two bodies by radiation process. Okay. So this one is the electrical analog formula. Some temperature difference by thermal resistance. You know this one. Okay. So F is the view factor or safe factor. It is depend upon the geometry of two surfaces, positioning of the two surfaces. So finally, there are 4 laws to explain the radiation phenomena or heat transfer through radiation. One is the Planck's law. It gives the emissive power at a particular wavelength. This is the formula. We have to remember this one to solve different numericals. Okay. So next is Stephen Boltzmann law. Total emissive power of a black body, not particular wavelength. Total emissive power of a black body. This is equal to sigma T to the power of 4. Okay. Next, Wayne's law. Okay. So this one is the maximum wavelength, where the radiation takes maximum value. Okay. So it means that is the at particular wavelength, the emitting energy is very high. So we can find that wavelength, or we can find that the temperature also, if you know that lambda max. Okay. So next one is the Kirchhoff law. We'll see what is Kirchhoff law. So Kirchhoff law, I will explain that one also. Here C1 and C2, these are the values you have to remember for solving the numericals. So this is the graph. So it means at particular wavelength, monochromatic emissive power EB lambda, so is maximum. Is maximum means derivative of EB lambda with respect to lambda is equal to 0. So at that position, so emissive power doesn't change with respect to wavelength. So by using this formula, you can find out the lambda max. Next, we'll see emissivity. What is emissivity? Emissivity is nothing but energy emitted from a surface, either gray surface, any surface. Okay, energy emitted from a surface to energy emitted by a black surface. So comparison of surface, any gray surface or any surface, energy emitted by that surface to energy emitted by black surface. The ratio of these two is nothing but emissivity. Okay, we will see what is Kirchhoff law. Just Kirchhoff law states the emissivity of the body. Emissivity of the body is always equal to absorptivity, and the body remains in thermal equilibrium with its surroundings. Okay, it means emissivity is equal to absorptivity. So absorbing energy. Okay. So for opaque surfaces means there is no transmissivity. Tau is equal to 0. It means there is absorption, there is reflection. Alpha plus rho is equal to 1. Okay. So for this one, alpha is the epsilon plus rho is equal to 1. Then epsilon is equal to 1 minus rho. Okay. Epsilon is equal to 1 minus reflectivity. Okay, diffuse surfaces we will see. The surface which its properties are independent of direction. Gray surfaces means properties are independent of wavelength, you can see. So these are the different laws which are used in the radiation process to find out the rate of heat transfer through the different surfaces, either black body or any surfaces. Okay, so these are the textbooks. You can refer textbooks to understand the concept of the radiation, mainly laws of the radiation. So thank you for listening this class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.